Good day, I'm Smriti Mahajan. Today we are going to talk about galaxies. Now, galaxies come in all shapes, sizes, and colors as shown in this montage of galaxies that you see here. These are all optical images of galaxies, and you will notice that some galaxies are very red. The ones which have the sun like orangish yellow glow are called red galaxies, while there are some galaxies which are very blue. Now, old stellar populations dominate the optical light from the red galaxies, while the blue ones have young hot blue stars forming in them. So, all galaxies in the universe can be classified into three categories by shape: the red elliptical galaxies, which are evolving passively, and the blue disk galaxies, which can either be spirals or irregulars. So, the spirals and irregulars are kind of flattened galaxies which have two of their dimensions larger than the third one. We live, for instance, in a spiral galaxy called the Milky Way. But do remember that this trend that the elliptical galaxies are red and spiral and irregular galaxies are blue is only a generic trend, which means that there are exceptions to this, but we will talk about them later. So, if you have to define a galaxy, how would you do it? And here is a collection from different sources, but you will see some terms being highlighted. For instance, Wikipedia tells me that a galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. The word galaxy is derived from the Greek word galaxias, which literally means milky, and hence the name Milky Way for our own galaxy. The NASA Space Place tells me that a galaxy is a huge collection of gas, dust, and of stars and their solar systems. A galaxy is held together by gravity. The Oxford Dictionary tells me that a system of millions or billions of stars, together with gas and dust, held together by gravitational attraction, is called a galaxy. My favorite one line statement often is that a galaxy is an amalgamation of stars, dust, and gas bound together by gravity. The takeaway point being that galaxies is not just stars, it has at least three distinct components: the stars, the dust, and the gas, which come together and interact with one another through gravitational force, and hence together compose a galaxy. Now, Edwin Hubble tried to quantify the morphology of galaxies using a scheme which we now call the Hubble's tuning fork diagram. As you can see, the spiral galaxies lie along the tongs of the fork, separated by the fact whether they host a bar at the center or not, while the elliptical galaxies lie along the handle, increasing in ellipticity from the far left end to the junction between the tongs. The junction between the tongs basically represent S0 galaxies, which we will talk about later, which are actually considered as a transitionary population of galaxies. Now, Edwin Hubble classified galaxies based on the observed ellipticity, E, which is defined as 1 minus the ratio of minor to the major axis. So the Hubble type of a galaxy is quoted as 10E, where E0 represents spherical morphology and E7 is highly flattened. Now, galaxies flatter than E greater than 0.7 are not observed, which basically means that elliptical galaxies with intrinsic ellipticities flatter than 0.7 do not exist. Among spiral galaxies, the SA types have the highest bulge to disk ratio of luminosities of the order of 0.3, while SCs have the lowest ratios of 0.05. What this basically implies is that the SA types have the most tightly wound arms and the smoothest distribution of stars in the arms, while the spiral arms of SC types are loosely wound and can often be resolved into star-forming clumps. We'll discuss this point in a minute. Typically, elliptical galaxies have masses in the range of 10 to the power 7 to 10 to the power 13 solar masses, and B band absolute magnitudes in the range of -8 to -23 magnitudes. The spiral galaxies, on the other hand, are generally massive with masses of 10 to the 9 to 10 to the power 12 solar masses and B band magnitudes of the order of -16 to -23 magnitudes. Here are some examples of the shapes of the galaxies which would fit the bill for each class in the Hubble scheme. Now, Milky Way is an SBC type of spiral, but it is still not clear whether it has a bar or not. Milky Way's bulge is also estimated to be pretty small, which with a radius of 2 to 3 kiloparsec. The Sun is at a distance of 8 kiloparsec from the galactic center. Most of the galaxies in dense regions of space, such as clusters of galaxies, are generally elliptical galaxies. Elliptical galaxies, as we've already said, mostly are evolving passively and hence have optically red colors. Even the metallicity of giant elliptical galaxies is very high, sometimes as much as twice the value of the solar metallicity. And some ellipticals are rotating very slowly, implying that these objects could collapse without flattening. Now, the surface brightness is the distribution of stellar luminosity as a function of the distance from the center, which means it's, in a layman's language, it is basically brightness of the galaxy as a function of r, where r is the distance measured from the center of the object. As seen in the images, the center is the brightest for the elliptical galaxies, and thereafter the luminosity per unit area will fall off as a function of r. For an elliptical galaxies, the surface brightness is given as L equals L naught e to the power minus r by r naught to the power 1 by 4, where L naught is a constant. It is generally of the order of 2 into 10 to the power 5 solar masses per square parsec, but it does have a large range. The range of R, which is also a characteristic radius, is very large. This particular form of the profile is sometimes referred to as the R1 by 4 law. The spirals can be classified into barred or unbarred galaxies, where bar is an oval or a rectangular structure, the kind that you see on top right image here, in accordance with the Hubble's classification scheme. The spirals can also be classified as grand design spirals. For instance, the galaxy that you see on the left top here, or flocculent spirals. The grand design spirals have very well defined spiral arms, while flocculent spirals look a bit diffused with many entangled short length spiral arms. The luminosity of spirals generally fall off exponentially, giving them an exponential light profile. The factor d is the luminosity scale length, which means it is the typical radius of a galaxy in the optical band and is usually taken to be of the order of 5 kiloparsec. S0 galaxies, as I've already told you, are the ones which appear at the node of the Turing fork in the Hubble's classification scheme. They are regarded as a transitionary class of galaxies in between that of spirals and ellipticals. The bulge in S0 galaxies is very large, almost comparable to the size of the disk. So they have a disk, but the disks are not as smooth as the spirals. Some of the S0 galaxies may contain dust and gas. suggesting that they are linked to spirals. The S0 galaxies are often thought of as transitionary galaxies or a transitionary phase where a spiral galaxy is becoming old and turning into elliptical. But we'll talk about that later. Apart from spiral and ellipticals, there are irregular galaxies. So obviously these are galaxies which are neither spirals nor ellipticals in shape. And there are some peculiar galaxies. The first two examples here are merger systems where two galaxies collided. They were initially probably spiral galaxies and they collided and they formed into some weird structure. Even the third galaxy was is a merger remnant. The fourth example here is what we call as the pinwheel galaxy, and the phenomena of a pinwheel is now pretty well understood, but we'll just not go into it. The takeaway point being that in this form, this galaxy is neither an elliptical or a spiral or an irregular. It's a unique galaxy in its own right. Now, coming to other properties of galaxies beyond morphology and luminosity, which is also synonymous for mass, galaxies can be classified on the basis of their color. In particular, the two-dimensional distribution in the color magnitude plane is used widely by astronomers. What you see on the plot on the right here is a distribution of the U minus R optical color of galaxies as a function of their stellar mass. And what is shown is the dominant morphological types that are likely to have those colors. So what you see is that as galaxies are becoming more massive, they are also becoming redder, which is the higher color. And as we expect, the shape is becoming more and more elliptical for more massive galaxies. Observations show that most red galaxies are elliptical while blue galaxies are disky. What you see here on the left panel is again the distribution of U minus R color for a complete sample of galaxies as a function of their stellar mass. And you see that there are at least two kinds of populations together here. The green lines separate those two populations. But when you actually separate out this sample into early type, which means elliptical galaxies, and late type, which means the spiral or irregular galaxies, the ellipticals actually lie along a sequence with very red colors, whereas blue galaxies are predominantly blue and low mass. Although you can also see from this figure that there are few non-negligible exceptions of blue ellipticals as well as red spiral galaxies. Now, as discussed earlier, the luminosity of extended objects is often measured in terms of their surface brightness, which is a measure of the concentration of light. Surface brightness is measured in magnitudes per square arc second. For typical nearby galaxies, it can range anywhere from 8 to 30 magnitudes per square arc second. But because we're talking in terms of log here, because we're talking about magnitudes, remember that a higher surface brightness would mean that the galaxy is more compact, meaning per unit area it has more light, and hence the surface brightness will be a lower number, and vice versa for a higher number for surface brightness. Surface brightness can be calculated by knowing the apparent magnitude as well as the radius for that galaxy. Now, the size of a galaxy can be defined in many different ways because a galaxy does not have a hard boundary, which means that the size of a galaxy will vary depending upon the wave band it is observed in and the depth of the image, which means how faint we can see in that particular image. So, here I introduce some terms which are often used when quantifying the size of the galaxy. The Holmberg radius is the projected length of the semi-major axis of an ellipsoid, which has an isophotal surface brightness of 26.5 B magnitude per arcsecond square. Effective radius is the projected radius containing half of the galaxy's light in a given waveband. The bulges of spiral galaxies typically follow the R1 by 4 law, which we've already discussed. But now, here, the de Vauquelin law is given in units of surface brightness rather than luminosity. The disks, the spiral disks in particular, are typically modeled with an exponential decay. So the spiral galaxies have an exponential profile. Now, to generalize these light profiles, bulges are some of, you remember that bulges are some of the densest stellar systems and they can be ellipsoidal, flat, or bar like. The surface brightness of spheroids or elliptical galaxies or bulges of spiral galaxies are often best fit using the Serschik fit. This is a general profile fit where the power of R by RE 1 over n, the n is called the Serschik index. N equals to 1 denotes an exponential profile. N is equal to 4, which means will give you back the R1 by 4 law, which is the de Vauquelin's profile. And then there could be intermediate Serschik values as well. Now, spiral galaxies, broadly speaking, though, will have 4 components. The bulge, which has a de Vauquelin's light profile, the disk having an exponential profile, and the halo, which is assumed to comprise of warm intergalactic medium, thus acting as a reservoir for cold gas, which keeps condensing into the disk and forms stars. Although all models of galaxy formation incorporate such a halo to feed cold gas into the disk, there are only tentative claims of their detection observationally. Last but not the least, as we have already discussed, there are globular clusters which surround the disk of the galaxies. The number of globular clusters around any spiral galaxy can vary a lot. The Milky Way, for instance, has anywhere between 125 to 200 globular clusters orbiting the galactic center. So now let's talk about how the spiral structure originates. Now if you look at the left top, there are 4 stars marked as A, B, C, D. Imagine all these stars lie along a line extending from the galactic center outwards. The stars will have roughly the same orbital speeds but will travel in orbits which have different sizes. In panel B, you will see that when star A has completed one orbit, stars B, C, D will only have completed one or less than one orbit. In panel C, you see that after one orbit of star A, the star B will be the next one to complete one orbit, then star C, then star D, and so on and so forth, and they will keep falling behind one another. After star A completes its second orbit, the spiral will continue to tightly wind around the galactic center. Now, this is how we believe that grand design spirals are created. The wave acts as a density wave moving in a galaxy, and the interstellar gas and dust which moves in the galaxy with much higher speeds relative to the density wave hit it and start forming stars. The interstellar gas and dust are moving with much higher speeds relative to the density wave. They hit it from behind, the gas gets compressed and starts forming stars. The stars are formed in front of the density wave. The stars are born on the spiral arm and will eventually venture away from it. But since the O and B stars are very short lived, they often evolve off before they can move too far away from the spiral arm. As a result, young stellar complexes are often found in close proximity of the density wave. But the low and intermediate mass stars can be found in the region between the spiral arms as well. These ideas are part of what is known as the density wave theory of formation of spiral galaxies. The flocculent spirals form in a slightly different ways. In slightly different ways. The rotation curve is the circular velocity of galaxies measured as a function of r. For a spherically symmetric system, we can very well approximate what this function would look like, because the gravitational acceleration at a distance r from the center of the galaxy is simply given as gm by r squared, where m is a function of r and is the mass interior to the radius r. So in this case, v squared by r is gm by r squared. As a result, circular velocity is given as square root of gm by r. Inverting this equation, we can then calculate the mass within a radius r as a function of the circular velocity squared r by g. G is a constant, r we can measure using the images, and circular velocity is now the one that we need to measure observationally. Now, gas and young stars in the disk of a spiral galaxy will move on nearly circular orbits, especially if the potential is truly axisymmetric. Therefore, if the bulk rotational velocity of gas and young stars can be measured, it will provide the circular velocity squared for the galaxies. In our own galaxy, the circular velocity at a distance of 8 kiloparsec from the galactic center, where our sun lies, is estimated to be 220 kilometers per second. Similarly, it can be done at other radii. Okay, but so what does all of this means? Now, for a solid velocity, one knows that the circular velocity is proportional to the radius r from the center of mass. For our solar system, which follows the Keplerian law, we know that the circular velocity is proportional to 1 over root r, and hence the curve looks something like the curve shown on the right here. But for a galaxy, the curve looks like the gray thick line in this image, which means it shows solid body-like rotation at small r's, and after that it shows a Keplerian-like rotation. But to measure rotational curves like this, we need to measure the mass within the radius r out to radii beyond 5 times, at least 5 times or greater than the effective radius. But the optical disk of galaxies is generally not this big, which means that we need the 21 centimeter H1 data. As you can see in this example of NGC 6964, if I take this image on same scale for the optical light coming from this galaxy and the radio 21 centimeter, the radio disk is at least 3 times larger than the optical disk. Let me show you some more examples of the same. This is galaxy M83. What you see here is the optical light and infrared light from stars and dust. But when the same thing is observed in the 21 centimeter light, you see all this emission shown in red color from the 21 centimeter radio emission. Here is another example of the merging galaxy pair M51. Once again, the optical light and then the extent of the H121 centimeter disk going much farther away than the optical disk. So naively speaking, what this means is that if stars were the only ones contributing to the total mass within radius r, after attaining a certain maxima as observed in the image, the rotation curve of the galaxy would have declined. But what we find actually is that rather than declining, the curve actually flattens out, or in some cases even rises, as you would see in this example where Vera Rubin used the 21 centimeter to map rotation curves of some of the nearby examples using long slit spectra. And because this curve is flattening, is telling you that there is much more matter at large radii from the galactic center than the luminous matter. As a result, this flattening of rotational curve is an observational indication of the presence of dark matter. I end this lecture here and will continue with more properties of galaxies in the next lecture. Thank you.